using Newton's second law. The results show that the net force is composed of both the weight force and the drag force when an object is dropped. I recorded a tennis ball being dropped from rest in the negative y direction. I also tilted my axes to account for the camera tilt. The data was recorded and plotted to get this graph. Alright, and a possible force acting on the system is the weight force from the Earth, and it's equal to the negative mass times the constant g in the direction that you set your y-axis to. We use this and other information gathered from the observed motion to create our first model. Our first model contains only the weight force, and the model, as you can see here, well, the weight force is added in right here, and the net force is set equal to only the weight force. And as you can see, the model overpredicts the position, meaning that there must be a force acting in the opposite direction to slow it down. Another observation is that as time progresses, the model gets more inaccurate. I aim to solve this problem by adding the drag force in, and the drag force is equal to negative b times the magnitude of the velocity squared. And it was added into the code right here. And we only had to worry about the y direction because that was the only direction that I focused on in my video, and it was also added to the net force right here. And the question is, what is b and how do you choose it? It's the proportionality constant that depends on the properties of that object. I chose it by trial and error and matching the model's final position with the observed motion's final position. And this is what it looks like when you run the code. And at first, the yellow weight force arrow is the only visible arrow, but as the velocity increases, the blue drag force arrow becomes larger. Also, as you can see, the graph was a pretty relative match. Let's see. And then this is a graph of the observed motion and the motion that included the weight and the drag force. And it's much more accurate, but as time progresses, the slope becomes more constant right here. And this shows the object reaching terminal velocity as the weight force remains constant, and as the air resistance continues to increase in the opposite direction, there's a point where the two forces become opposite and equal to each other and cancel each other out, creating a constant speed or an F net of 0. And for the what if questions, okay, it asks what if the object was initially thrown down instead of dropped from rest? Would the terminal velocity be the same or different? And it would be the same, it would just take less time to reach the terminal velocity if it was thrown down. Because if you remember the yellow arrow for the weight force arrow, the magnitude stayed constant. And it would do the same even if it was thrown down. And question number 2, what does it mean? Okay, the graph and the weight force only showed, they showed a much more rapid decline, but the graph of the weight force and the drag force together began to reach terminal velocity, which means the slope of the graph velocity over time would be close to a straight line as time progressed. And this makes sense because the two forces become equal and opposite to each other, canceling each other out. Thank you.